Hello and welcome to the solution guide for Moon River by my dad Bellal and myself, the pedaling pianist. Now, to be honest, this was mostly my creation, but my dad did contribute one of the clues and some really lovely ideas around it. And to be honest, I don't mind giving him some extra credit anyway for turning me into a puzzling geek in the first place. Now, if you're wondering why I called it Moon River, honestly, so am I. I'm not very good with names, but I will leave something resembling an explanation in the video description. For now though, let's get on with the rules. Normal Sudoku, disjoint groups, arrow, little killer and palindrome rules apply. Additionally, digits in each cage must sum to n, where n is the same for every cage. So these three sum to n, these three sum to n, those two sum to n, and those three sum to n. And then the rest of the rules just explains what these normal rules are. I'm not going to go through all of them because if you're watching this video, you probably know most of them anyway. I will just scroll slowly through them so you can read if you need to. The one that you just do need to remember is the disjoint groups rule, because that's not immediately obvious from the visual presentation of the grid. Anyway, without further ado, let's get on with the solution. So the first thing to do is to highlight both of these little killer diagonals. So what this is saying is that these two together must sum to 57 plus 58, which is 115. You might be thinking that's suspiciously high. Well, you're right. So let's see what the most we can make our yellow region is. Let's start with these two cells. What's the highest we can make each of these cells? Well, they can't be 9 because they're on an arrow, and if we made either of them 9, then this would become at least 10. So the highest they could be would be an 8, with a 1 here and a 9 in the arrow head. But as soon as we made this an 8, this can't be an 8 anymore because of the disjoint rule. It's in the top right position within its box. So this now becomes a maximum of 7 with a 2 to sum to 9. So that is the highest that we can make those two, i.e. together 15. We could swap them round and put the 8 up here and the 7 down there, but in the end we will still end up with a total of 15. These 5 yellow cells are a maximum of 9, 8, 7, 6 and 5, which sums to 35. Same with these 5, and then these 5 in the middle, because we can't have a 9, are a maximum of 8, 7, 6, 5 and 4, which sums to 30. So 35 plus 30 plus 35 plus 15 equals exactly 115. That's exactly the total we need. Now, is there any wriggle room? We could make this total higher. At the moment, we're just proposing that it's going to be 4, 5, 6, 7 and 8. Well, we could make it 4, 5, 6, 7 and 9 to make it sum to 31 instead of just 30. That gives us 1 extra in our yellow total. But by doing that, this can't be a 9 anymore. It's reduced to a maximum of 8. Therefore, this is reduced to a maximum of 7 and 6. So even though we've added 1 to our potential yellow total in box 5, we've taken 2 away from our potential yellow total in these two cells because they're now a maximum of 13 rather than 15. And so our total maximum for yellow is now only 114. If we make this any lower, we can make this higher, but again, we are just damaging our yellow total even more. So that can't be the case. It must be exactly like this. Although we don't actually know which way round these are. It's a 7-8 pair, this must be a 1-2 pair, this must be a 9, this must be 4, 5, 6, 7, 8. I won't actually leave that in, but I will leave the remaining digits in the box in as pencil marks, 1, 2 and 3, and then here we must have 5, 6, 7, 8 and 9, so the remaining digits must be 1, 2, 3 and 4. Now, you may have noticed that we have now got a quadruple in the top middle positions of each box. So those 4 positions I've highlighted are all in the top middle, so they must all be different, otherwise they will break the disjoint groups rule. They must be the digits 1, 2, 3 and 4, exactly once each. Within that quadruple, we must have a 4 either here or here. So I'm going to notate that like this for now, which is a little bit misleading, but I promise it will be useful in a moment. Because we can say exactly the same thing about the middle right positions. We've got another quadruple on middle rights of 1, 2, 3 and 4, and again, within those positions, the 4 must go here or here. Now we have a weird kind of X-wing on 4s, in the sense that we know that one of those two must be a 4, and one of those two must be a 4. So if out of those two, this one ends up being the 4, then out of those two, it must be the one in box 9 that ends up being the 4. So we get 4s there and there. Or alternatively, if out of those two it's this that ends up being the 4, then out of these two it can't be the one in box 9 anymore, so it must be that one. So we will end up with 4s here and here, or here and here, which means that we cannot have any extra 4s in boxes 1 or 9, so those 4s come out. Another thing we can do with the 1, 2, 3, 4 quadruple in the top middle position is say that this cell now must be at least a 5, because it can't be 1, 2, 3 or 4, otherwise it will break the quadruple within the top middle position. So that's at least a 5, I'll notate that like that for now. And again, we can say exactly the same thing about the middle right position. This cell now must also be at least a 5. What you will notice through a lot of this solution, certainly the first half of it, is that it's completely symmetrical around this positive diagonal axis. And so most of the logic that we do, we can kind of do twice in a kind of symmetrical, reflective way. Now that these two cells are at least 5 each, can this cell also be at least 5? Well, if they're all at least 5, then the minimum they can be is 5, 6 and 7, which sums to 18. So can n be 18? And the answer is no, because of this cage here. The maximum we can make this cage is an 8 and a 9, which is only 17. So we must have at least one digit in this cage that is less than 5. It can't be that or that. Let's just take these out, actually, that's not going to be necessarily correct. It can't be that or that that's less than 5, so it must be this cell that's less than 5, except we already have a 1, 2, 3 triple in the top right positions of boxes, so it can't be a 1, 2 or 3, it must be less than 5, it must therefore be a 4, and that knocks 4s out of these positions and places them here and here. Right, let's ask where the 1s, 2s and 3s go along row 1. They can't go there because of the 1, 2, 3 triple in the box. They can't go there because that's a 4. We do have 1 there, so in these 6 cells we must have 2 of the digits 1, 2 and 3. Except we've already got a triple on 1s, 2s and 3s in the top middle positions and in the top right positions, so these can't be 1s, 2s or 3s, and therefore the only remaining cells that can be 1s, 2s and 3s in row 1 are those two, and that must therefore be where they go. And again, the logic is completely symmetrical for column 9. We can't put 1, 2 and 3 there or there. We do have 1 there. We can't put any more in middle right positions or top right positions, and so these all end up being our 1, 2, 3 triple. We can also look closer at the top right positions in general. We already have the 1s, 2s and 3s accounted for, the 7s and 8s accounted for, and the 4 accounted for, so these 3 cells become a 5, 6, 9 triple. It's at this point that we can start to analyse this palindrome. It's not telling us much, it's only telling us that those 2 digits are the same. So let's analyse all of them and rule them out by process of elimination. The first 3 digits we're going to rule out are 1, 2 and 3. The logic is exactly the same for all 3. Let's just pretend it's going to be a 1. So can we put 1s in those 2 positions? And the answer is no, because in the top row we can't have a 1 there because of that 1 in the column, we can't have a 1 there because of the 1 in the box, so the 1 must go exactly there in the top right position of box 1. By completely symmetrical logic, that can't be a 1 and that can't be a 1 by normal Sudoku, so that becomes a 1, and then we have 2 1s in top right positions of boxes. In fact, we have 3, because in box 5 the 1 will be forced there as well. So that breaks, and exactly the same logic is true for the 2s and 3s, because obviously these 1, 2, 3 triples work in the same way for all 3 of the numbers. So we can immediately rule out 1, 2 and 3 from those positions. We'll come back to 4, that might be a little bit of a spoiler. Let's look at 5 and 6. So, and also 9 actually. Can we put 5, 6 or 9 into these positions? If we do, then within this 5, 6, 9 triple, let's just say it's 5. So if we put 5 here and here, then within the 5, 6, 9 triple, the 5 must go there by normal Sudoku. Then in box 1, where does it go? Well, by normal Sudoku, it's there or there, and by disjoint, it can't be in the middle left position, so it goes in the middle. And in box 9, by normal Sudoku, it goes there or there, and by disjoint, it can't go in the bottom middle position, so it goes in the middle again. And we get a clash of whatever digit we're talking about, 5, 6 or 9, in the middle of boxes 1 and 9. So 5, 6 and 9 can all come out. Now, you may have noticed about this palindrome that the positions of these cells are the bottom middle position and the middle left position. Those are the positions of all of the remaining cells on our 58 diagonal, now that we've got this 15 here. So we know that these are going to be a 7-8 pair, so they will add to 15. So these remaining 6 digits must add up to exactly 43. So we could start asking, can we not put an 8, for example, on this 58 diagonal? Because if we put an 8 here and here, that's ruling out all of the bottom middle positions and all of the middle left positions, and so we would not be able to put any more 8s along the 58 diagonal. And we can ask the same question about 7s. So let's start investigating those possibilities. Now, the first question to ask is, can we not put any 9s along this diagonal? Well, if we don't, then you might be tempted to say that the maximum that we could put on that diagonal would be a 7-8 pair there, a 7-8 pair there, and a 7-8 pair there. But that breaks, because we can put a 7 and an 8 like that, and an 8 and a 7 like that, but then the middle bottom and the middle left positions are both ruled out for 8 and for 7, so this could not be either. So actually we can never put more than 2 of the same digit along this diagonal in these 6 cells. So actually the most we could put in these 6 cells, if we're not using a 9, would be an 8, 7, 6, 8, 7, 6. Something like that, where we have 2 8s, 2 7s and 2 6s. That sums to 42, which when added to 15 is only 57. So that does not make the total up, unfortunately. So we do need a 9. We do need at least one 9 to go into this diagonal. Can we have 2? And the answer to that is no, and this is not particularly easy to see, but I'll go through it. Obviously we can't have a 9 there or there because of the 9 in the box, so if we had 2 9s along this diagonal, they would go in box 1 and they would go in box 9. Now, where are you going to put a 9 in column 3? It's not going to be in box 1, it's not going to be there or there, it's not going to be there because of the 9 in the row, it's not 4, so we must have a 9 in those positions in box 7. Where are you going to put a 9? In row 7. See, this is the thing about this puzzle. Some of these deductions are very hard to spot, but once you've spotted it once, you can then use the same logic twice, just reflected around the positive diagonal axis. You can't put it in box 9 anymore because we're hypothecating a 9 goes in one of those 2 positions. Those aren't 9, that's not a 9 because of the 9 in the column, 4 does not equal 9, so we must have a 9 in box 7 in one of those positions. So if we do end up putting 9s there and there, we end up with 2 9s in box 7, so that is not allowed. We must hold Control Z for a while, and yes, we've got rid of all of our 9s. Good. So we must have at least 1, but less than 2 9s, fewer than 2, I suppose, along this diagonal. So there must be exactly 1 9 along this diagonal. Bearing that in mind, can we get away with putting no 8s along that diagonal? Well, if we put no 8s along that diagonal, the maximum we can make it, given that we can only have a maximum of 2 of each digit in those 6 cells, would be a 9, the 9 that we already know we must have, 2 7s, 2 6s, and a 5. That sums to 40, which, when added to our 15, is only 55, so that's not enough. So we must have at least 1 8 in these positions. And therefore we can't have 8s in both of those positions because that would break the diagonal. That would rule a 8 out of all of those diagonal positions. Can we get away with not putting any 7s on this diagonal? Well, if we don't, then the maximum we can make those 6 cells would be the 9 that we know must go in those 6 cells, 2 8s, 2 6s, and a 5. That sums to 42, which when added to this 7-8 pair gets us to 57 again. So again, it just misses out, and we can conclude that we must have at least 1 7 in these 6 cells, which therefore tells us this cannot be 7. And finally, after some pretty hard work on the palindrome, but pretty satisfying work I think once you found it, we can finally put 4s into those positions. We now have 4 4s looking into box 3, so that becomes a 4. Now let's think about n. From this cage we know that these 2 cells are both a minimum of 5, so the lowest we could make both of them together would be a 5 and a 6. 5 plus 6 plus the 4 we already have is 15, so n must be at least 15. Well, can that be a 1 then? If that's a 1, that must be at least 10, so it's not going to be a 1. If that's a 2, that must be 9 to make it sum to 15, and if that's a 3, it could be 8 to make it sum to 15, or it could be another 9, because we know that this cage is not exactly 15 necessarily, it's at least 15. So actually, from this we now know that the most we can make n is 3 plus 9 plus 4, which is 16. So we've narrowed down our options to 15 or 16. Now we can look back at this cage and say, well, if it's 15, those 2 must be a 5 and a 6, as we've already kind of discussed. And if it's 16, then those 2 add to 12 using digits that are at least 5 each, so it must be a 5 and a 7. Either way, we definitely have a 5 in there. This cage works exactly the same way as this one. These must be 5, 6 and 7, but definitely 5. Now, this cell cannot be a 5 because then that would have to be a 10 or an 11. So we take 5 out of there, and now in the top right positions of boxes, the only place a 5 can go is here or here. So there must be a 5 in one of those two. That therefore can no longer be a 5, and this must be a 5. Now we can ask, can that be a 2? If that's a 2, that must be a 9 to bring n up to our minimum total of 15. Also, this must be a 6 because we now know that n is 15, so that must be 6 to complete that cage. So we get a 6 there, a 9 there, and then these both become 5s, and row 1 is broken. So this cannot be a 2, it instead becomes a 3. This still doesn't tell us whether n is 15 or 16, but it does give us loads we can start doing with the 1, 2, 3 triples. We can take 3s out of these positions. We can also take a 3 out of here, because this digit must repeat in box 1 in the 1, 2, 3 triple, but it can't be in the same column as that one, so it must go here. That means the only place for a 3 in box 1 is there. Now we can start colouring our 1s and 2s. We know that these must be different. Let's do red and blue. That can't be red, so it's blue. This can't be blue, so it's red. This can't be red, so it's blue. Now, we know that this 7 and 8 is different because of the disjoint rules, so these 1 and 2 must be different, so that they both end up summing to 9 correctly. So that must be red. Now, in this 1, 2, 3 triple, red must go exactly here. In this box, red goes in one of these 3 positions by normal Sudoku. I've realised I've missed a step, but let's just carry on for now. It can't go in the top middle position because of this red just here. Where did it go? So let's just put red in one of these positions. Where does it go in box 5? It can't go there by normal Sudoku, and it can't go there by disjoint because of this red in the top corner. So that becomes red, and that's the step that I realised I missed. This is therefore going to be our red. That's not a 3 anymore. Now there are 4 reds looking into box 2, so that the only position for it is here. Let's fill that in. In this box, the only 2 positions we can put red in by normal Sudoku are those 2, and the top middle is ruled out by that one, by disjoint, so that becomes red, and our final red is just here. Now let's do some bluage. There's a blue just here. In box 3, blue goes there or there by normal Sudoku, but not there because of the disjoint rule, so that's blue. In box 5 it's here, so in box 6 it must be along the bottom row, and it can't be there, and it's not red, so that's blue. Oh, whoops, that's blue. Now in this 1, 2, 3 triple, that must be blue, which actually tells us this is a 3. What blues am I missing? I think it's just a blue here or here, and the disjoint tells us that it must be in the middle, and therefore our final blue goes here. So that becomes a 3. We can also put a 3 into here by normal Sudoku, and a 3 into here by normal Sudoku by asking where it goes in this column. Now that we've done that, we can actually look at the 4s. The 4s were almost finished before. We had a 4 either there or there, and now that we know that there's a red digit there, we can finish off the 4s by putting them there, there, and there. Now, the next step is not easy to spot, and it's probably the closest that this puzzle gets to bifurcation, but I don't think it's too bad. What you need to do is ask if this can be a 6. Well, if it is a 6, we know that this sums to either 15 or 16, so that's either a 9 or a 10. It's obviously not going to be a 10, so it becomes a 9. Along with this 9, we end up with a 9 just here, in box 4. In box 1, it must go there. And now by normal Sudoku, the only place left for a 9 in box 3 is here. But this breaks for 2 reasons. And I think that makes it a little bit more justified that it's somewhat bifurcatory, because if you do get to this stage, you're twice as likely to notice that this breaks. Firstly, it breaks by disjoint because we have 2 top middle 9s. And secondly, it breaks because of the n rule. By making this a 6 and a 9, n becomes 15, but by making that a 9, n becomes 16. So either way, we find that it breaks if you put a 6 here. So we must put a 9 here. By putting a 9 here, we can no longer have any more 9s in top right positions, so they come out. That gives us a 5-6 pair in the top row, which means this becomes a 7, and finally we have worked out that n must be 16. That means we can fill this in as 9, this becomes 7, and this becomes a 5-7 pair to correct that cage, except this 7 by disjoint tells us that the 5 and the 7 go this way round. Now the 7 will resolve this 7-8 pair, that becomes 8, that becomes 7, that tells us that blue must be 2 and red must be 1. Now, from this point onwards, it turns out you only actually need normal Sudoku and the disjoint groups rule to solve the rest of the puzzle. I'm a little bit disappointed by that, because until this morning, when I played it through, I thought that it was still necessary to look at this 58 diagonal and do a little bit of maths to work out that these 5 digits must be a 9, 2 8s, a 7 and a 6. Now that can help you if you want to take that particular solution path, but I'm just going to use normal Sudoku and disjoint groups, and I'm going to start by placing an 8 in the top row to finish off the row. Now I'm going to look at column 6 and ask where a 3 goes. It can't go anywhere where we've already got things that aren't 3. It can't go in box 5 because of that 3, it can't go there because of that 3, and it also can't go there because of that 3, because of it's in a middle right position, so that becomes a 3. Now, where does a 7 go in this column? It can't go anywhere where we've already got stuff, and it can't go in any middle right positions because of this 7, so those two are ruled out, and that becomes a 7. Now in this box, an 8 can't go down the middle, it gets shunted over there. In this row, we can no longer have any 8s in top middle positions because of this 8 just here, so the only position left for it is there. Now in box 4, an 8 has to go in there. This becomes a 5-6 pair. In box 3, there is a 7 either here or here, which means that in box 2 it must go, well, not there because of that 7, it has to go exactly there. Now we need a 9 to complete the column, and we get another 9 just here as well. In this column we need a 6 and a 9, that has to be the 6 because of that 9 just there. That becomes a 9 as well. That is another 5-6 pair. This is a 6-8 pair. This is a 5-6 pair, but that 6-8 pair resolves it. That becomes 5, that becomes 6, that becomes 5, that's a 6, that's a 5. This is a 6-9 pair, but that 6-8 pair resolves it. We get the 6 there and the 9 there. This is a naked single, it sees every digit except for 9. That leaves a 3 and an 8 to complete the column. We need 5 and 6 in this row, but that 5 tells us it's this way round. That resolves this 5-6 pair and that one at the top. That 6 resolves the 6-8 pair. That puts an 8 at the end of this column. We need a 5 and a 7 here, and that 5 tells us which way round. We need a 5 to complete that column, a 9 to complete that column, 6 to complete that column. This becomes a 3-7, and this becomes a 7-8. And wouldn't it be really lovely if we had to use these little killer clues to disambiguate this 7-8 and therefore this apparently deadly pattern that we've got left? But unfortunately, well, you can use those if you like, or you can use some disjoint logic with these 7s and 8s. Let's use this 8 to tell us that that's not an 8, so it must be a 7. That's an 8, 8, 3, 3, 7, and unfortunately no 3s in the corner for this puzzle. Anyway, thank you very much for watching. I hope you enjoyed the solution. Do let me know in the comments how you got on, and I'll see you next time.